The objective of our project is to calculate the losses of energy due to friction between a Hot Wheels car and a downward track of variable height. We will accomplish this objective by calculating velocity and height of the track. With these values known, we can find the potential energy at the top of the track and the kinetic energy at the end of the test. The difference between these two values will result in the energy loss due to friction. Further, we will calculate the coefficient of friction between the Hot Wheels cars and the track with our known values. Knowing coefficient of friction, we can further assess the performance of the different vehicles. To further describe the objective of our project, I've drawn a diagram. At the top, we have our car, which will be pushed down with unknown velocity. First, we must find the gravitational potential energy at the top of the track where the car starts. As the car travels down the track, it will gain kinetic energy, although as it travels, it will lose energy due to friction. Therefore, the difference between the gravitational potential energy and the kinetic energy at the bottom will result in the energy loss due to friction.
For our project, we'll be using two sensors, one of which is a strain gauge. A strain gauge works by measuring strain in a solid body. It's made from a fine metallic foil element set into a grid-like pattern and placed on a thin backing called a carrier. The strain gauge is a sensor which measures resistance with an applied force. It is able to convert values such as force, pressure, tension, and weight into electrical signals which we can read using the DAC. The second sensor we'll be using in our project is the light sensor. A light sensor senses light. To do this, it uses a silicon photodiode to translate light into current. When a photon of light comes in contact with the sensor, it excites the electrons within the sensor, generating a microampere current, which can be then read by the DAC.
So for the building blocks of our system, we'll be using two light sensors to measure the velocity, and then a strain gauge which will be calibrated with 1 kg of mass. The signals from these sensors will then be amplified and then read out using the data acquisition system.
So when a car is placed on our track, it will result in a deformation which will be recorded by the strain gauge. The strain gauge can be used to calculate mass through a calibration process. By using multiple different known masses to deform the strain gauge, we can create a plot of our data to predict the mass of a toy car. So in order to measure the speed of our car, we'll be using two light sensors which will be placed a known distance apart to measure the time it takes for the car to get from the first sensor to the second. With this data, we'll have the variables distance and time to calculate the velocity of our car.
Application: calculating energy loss due to friction and the coefficient of friction to validate our results. If we achieve similar coefficient of friction values for multiple cars of different mass and length, we can confirm that our sensing is accurate and effective. Application in real life would be simulations for different traffic track conditions such as sandy tracks, water, icy tracks, to gain data on current automotive tire technology.